Okay, so now indifference curves, continuing from the previous video. So our utility function u of quantity 1, quantity 2 is two variables, hence we have a 3D graph. As you know, it is useful to use level curves. What is this? If we're looking at a map, it is contour lines. A level curve, a contour line, is just a line such that every point is the same height up off of the page. To translate this 3D graph into a 2D graph that is easier to work with. For example, figure 4.2 depicts some level curves of the Cobb-Douglas utility function. So they give us the function and they show some of the level curves. If it's very obvious to us, that's good, but these are the simplest concepts that we don't really need. This is Q2, this is Q1. So straight out of the page, it's not a physics class, but if you have a math or physics or calculus 3 class, they sometimes do a little dot, meaning an arrow staring straight at us, but uh, we don't need this either, but this is kind of a more depiction over here. Not a very good one, but this is Q1, Q2 in the two-dimensional plane, where everything is perpendicular to each other. And then, of course, out of the page would be U, the function of Q1 comma Q2. So it's just basically that one thing where we only look down at the two-dimensional plane. And of course, it's impossible, with kind of the tool we have to draw the three-dimensional graph through the whole class, we'll never need the three-dimensional graph. If you look at the three-dimensional graph, we did this in chapter 2, going out from the origin, uh, the uh, they are the indifference curves in this chapter. There's like 3 different names for them. In chapter 4, they're indifference curves. Chapter 3, they're isoquants, and then chapter 2, they're just going to be contour lines. Yeah, but as we go further from the origin out, we go up to a higher utility. So our utility, our preference is better. Yeah, the more we go out, our U is 40 right here. Our U is 60. That's our preference. We don't like to say happiness. We like to say preference, but that's basically our happiness or a less money stress or something in the world, a place that we would prefer to be. Yeah. So all the same concepts as there always were. It's a it's a contour line. It is a line such that every point on that line is at the same height. Therefore, it's all the possible values of Q1 and Q2 such that U equals 60. If Q1 drops to this, and they talk about all that, how you can exchange. I don't like to talk about the slope like that. It's just basically algebra 1, algebra 2, understanding all the way up until today, but there's a lot of fancy ways to describe the slope, and they're just talking about the slope when they talk about trading Q1 for Q2 or Q2 for Q1. But if we reduce Q1 to that, and if Q2 increases to that, then we're on the same indifference curve. Yeah. Indifference means we're indifferent to the combinations of Q1 or Q2 in our basket there. Notice how 3, 4 times in a row I just end up repeating myself because there's more one way to say it. But we do want to notice those things is that the indifference curve is all the infinitely many combinations of quantity 1 or quantity 2 such that our U is the same, and we want to observe the second thing, that we are looking to get as far away from the origin as we possibly can. So if we make it another curve out here, it gets a little bit cramped in there, but if we make another one such that U is 100, it's better than U 80. Yeah. Okay, so that's it. That's what the indifference curve is. It's that and only that for the Cobb-Douglas, and they're going to have the 3, the Cobb-Douglas, the linear, linear is perfect substitutes, and the L shape, which is perfect complements, but the Cobb-Douglas I think we find to be most important. We call it an indifference curve. Each indifference curve connects all the baskets, commodity bundles, Q1, Q2, that results in the same utility level. Therefore, the consumer is indifferent between all baskets along the same indifference curves. Can you predict what we will say next? Stop to think about it. Okay, so the MRS is the marginal rate of substitution. We could read through all this thoroughly. I'll always kind of browse through. That way we can definitely stop and read if we want, but I notice pretty quick that if I'm reading aloud, it's a waste of time. But we can kind of read this stuff, and I'm just kind of summing up here. But the marginal rate of substitution, which yes, was from chapter 3, we're now in 4, marginal rate of substitution. Yeah, there they are. It's going to be the absolute value of the slope. Yeah, so remember, Cobb-Douglas, the slope is always negative. Yeah, but if you take the slope, what is the slope? We're going to talk about all these little things. It is Q2 as a function of Q1 is the convention. That just means it's the way it's often done. But we don't want to talk about it here because I'm off point. But if you do it the opposite, it is fine and it is the exact same thing. But however you do it, it's always this. Q2 is a function of Q1. We will discuss that in a moment. However you do it, what is a slope? The slope would be the change, the rise over a run. I know that that's more like technically an average slope. We're not talking about that. The slope would be the derivative. Yeah. Okay, so it is correct that the MRS, which is the marginal rate of substitution, is always positive. We can call it an absolute value, which mathematically I don't like to say absolute value because it's cheating. It is true that it's the absolute value of a negative, but if the slope is negative, I would always prefer to say that it's the negative negative. If the slope is negative, then negative that is positive. So the MRS is just going to be the slope, and we're just defining that point. Remember, I said in 1 or 2 videos ago, we're just defining that from the last video. I'm always getting ahead of myself there, where the slopes are the same. But the MRS is the marginal rate of substitution because you can trade sum of Q2 for Q1, Q1, Q2 stand the same thing. And the MRS is always going to be positive, therefore negative the slope because the slope is always going to be negative. So we can go through an example and all that, but it's just all very obvious stuff and it's review from chapter 2 and 3. Okay, so we don't care about that from equation 2.4. That goes back into chapter 2, like we just said. Chapter 2, 3, and 4, very similar. 2 is an introduction, but 3 and 4, at least these 10 pages I describe are exactly the same. And then that second half, 10 pages, is actually going to be quite different than chapter 3. But the first 10 pages derivation here are a repeat of chapter 3. Okay, so we have this thing right here, yes? So we can write the whole thing. I can read through, but I don't need to. So if we have MRS, I think I'll probably say it later. I try and explain something, then a thought crosses my head. But let's just go ahead and say the whole thing. We always, not always, yeah, but besides that, we always have Q2 as a function of Q1. Can you flip the convention? You actually absolutely can, yeah. But this MRS, we're talking only notation, not math, is always going to be X comma Y. That's right. So if Q2 is the Y axis, it's always going to be MRS. We said X comma Y, so it has to be 1 comma 2. So we're literally just saying that this notation, this subscript, always goes to this graph. Obviously, you can flip it, and then it's not like it changes. It's just then we're obligated to say MRS 2 comma 1. It's a technicality where it is a convention that we have to obey. So 1 comma 2 does refer to quantity 2 as a function of quantity 1. Okay, so that being said, blah, blah, blah. The one that we 90 or 100% of the time use is MRS. This takes just a minute, so if we can, let's kind of just do this in the next video here.